Hello students and welcome to our very first video lecture for our Hybrid Chem 213 class, the second semester of organic chemistry. For the first 2 weeks of this class, we're going to start by reviewing what you learned in Chem 212. And for this lecture, it's going to come in two parts, about half an hour to 45 minutes apiece. And is going to review chapters 1 through 6 of your textbook. And then next week, we will review the remaining parts of Chem 212. A little bit lighter this week, as it's our first week and you've got lots to do. And then we will fill this out for the second week and get you all up to speed and remembering everything you need to know as we move into Chem 213. So let's get started. Oops. So we're going to start by reviewing what you would know from general chemistry, what we learned in chapter 1, which is all about general chemistry. And what's one aspect that's very, very important is the formal charge of atoms in molecular structures. This is a record-keeping type of thing so that we know, and I'm in the way a little bit, but so that we know what we're basically keeping track of where the electrons are located in a molecule. And so for a neutral, for a carbon atom that has zero formal charge, it's generally making 4 bonds and has no lone pairs. That's because carbon starts with 4 valence electrons, needs 4 more to have 8 and a full valence shell, so it tends to make 4 bonds. Likewise, nitrogen starts with 5 valence electrons as a neutral atom. Being in group 5 of the periodic table, needs 3 more to have 8, so it tends to make 3 bonds and it has 1 lone pair. Oxygen tends to make 2 bonds and has 2 lone pairs. And halogen atoms, including fluorine, chlorine, bromine, iodine, tend to make 1 bond and have 3 lone pairs. And if this differs, on the left side here, we see atoms in which we have 1 less bond and 1 more lone pair. So this carbon here has it has 3 bonds instead of 4, and it has a lone pair, which it didn't have. So that indicates an additional electron. That's a -1 formal charge. Likewise, relative to the 0 formal charge nitrogen, this has 2 bonds and 1 lone pair. So this is a -1 formal charge nitrogen. This would also be true if it were a double bond rather than 2 single bonds. It's just how many bonds, basically. This oxygen, instead of having 2 bonds, has 1 and an additional lone pair, so negative formal charge. And here there's a fluoride ion with 0 bonds and 1 more lone pair, and so it has a negative formal charge. On the other side, if you have 1 more bond and are lacking a lone pair, so in the case of this nitrogen, instead of having 3 bonds and 1 lone pair, it has 4 bonds, that's a positive formal charge. For the oxygen, having 3 bonds and 1 lone pair instead of 2 bonds and 2 lone pairs is a positive 1 formal charge. And in these cases, these are kind of special situations, but if a carbon has 3 bonds instead of 4, that's like losing 1 electron, the one that would have been in this bond, 1 out of the 2. And so it also has a positive formal charge, and the fluoride without its bond would also have a positive formal charge, and any halogen. So this is the quickie way of calculating formal charges. There's a more complex way as well, but this usually suffices for our purposes. And formal charge is just a way of keeping track of molecules, a hypothetical charge that we give it, or keeping track of electrons, rather. So for example, if we're looking here, what would be the formal charge on each of these? Okay, in the case of the oxygen here, this is an oxygen with 3 bonds and only 1 lone pair instead of 2 bonds and 2 lone pairs. So this is going to be, if we go back to the slide, the previous slide here, this is going to be the situation where the oxygen has 3 bonds and 1 lone pair. It is lacking 1 bond, so that makes it, or lacking 1 lone pair rather, it's basically lost an electron, so it has a positive formal charge. And then here we have a carbon. Now this carbon, it has 3 bonds. There's a hydrogen that's not drawn, but it has 3 bonds and 1 lone pair, so that gives it a -1 formal charge. Here, this oxygen has 2 bonds and 2 lone pairs, so it has no formal charge to it. This phosphorus is below nitrogen, in the same group as nitrogen, so it works the same way as nitrogen. Here it has 4 bonds and no lone pairs, so that gives it a +1 formal charge because it should have a lone pair. And then this one has, instead of one lone pair and 3 bonds, it has 2 lone pairs and 2 bonds, meaning it has an extra electron, giving it a -1 formal charge. And so that's a quickie way of assigning formal charge, and you need to be very, very comfortable with doing this quickly. Basically, what you saw in that last slide, this should be in your brain by now. And if it's not, make sure to understand why it's the case. Essentially, these all have 1 extra electron on the left here, and these guys on the right are lacking an electron due to having 1 less lone pair and 1 more bond, or just here having 1 less bond in this case, and in this case. So you don't have to memorize them per se. You should understand why the way they are so that you can very quickly spot formal charges. Likewise, if you see a carbon with a -1 formal charge, you know it must have 3 bonds and 1 lone pair. So if you're given the formal charge and not the lone pairs, you should be able to get those as well. When it comes to bonds, bonds may be polar. Both bonds are considered polar if they're containing 2 atoms that have significantly differing electronegativities. And so the electronegativities here increase as we go to the top right. They're the highest 4 atoms at the top right. And the threshold here, we say that bonds are polar if their electronegativity difference, the difference in electronegativity between 2 atoms is 0.5 or greater. Now, that is not to say that those atoms with electronegativity difference of 0.4, for example, carbon and hydrogen here, are not at all polar, but they're not very polar, and so we consider them not polar. And a completely nonpolar bond would be between 2 atoms with exactly the same electronegativity, such as 2 of the same atoms. So the greater the difference in electronegativity, the more polar the bond, and this is important because molecules with polar bonds, depending on their geometry, may be polar molecules, and that affects their physical properties and chemical properties. When it comes to bonding, bonding can be described by the overlap of hybridized orbitals, and this is referred to as valence bond theory. And valence bond theory says when 2 orbitals overlap in this way, we make what's called a sigma bond. And so here we have a sigma bond between hydrogen and a orbital in carbon here, which happens to be what's called an sp hybridized orbital. And here's a direct overlap between 2 of carbon's orbitals, these gray ones. And then here's an overlap between hydrogen's 1s atomic orbital and carbon's sp hybridized orbital here. And these are called sigma bonds due to the direct overlap. Pi bonds are due to sideways overlap of unhybridized orbitals. And we'll talk about how to recognize these hybridized orbitals, but generally atoms will have 1s atomic orbital and 3p atomic orbitals, 3p atomic orbitals. And when bonding occurs, these orbitals may be hybridized, meaning mixed to make equivalent orbitals. So in the case of this molecule here, which happens to be ethine, each carbon is sp hybridized, and we can tell because it has 2 sigma bonds here, a bond here going to the hydrogen and a bond going to the other carbon with direct overlap, and so it needs 2 orbitals. These would be sp hybridized. If it needs 3, they'll be sp2 hybridized, meaning 1 s orbital is hybridized with 2 of the p orbitals. If it needs 4 equivalent bonding orbitals for sigma bonds, it will contain 1 s orbital and 3 p orbitals for an sp3 hybridized. In this case, it's sp hybridized, meaning that there are 2 unhybridized p orbitals remaining because only 1 of the 3 p orbitals was used up. And so these are those p orbitals, each containing an electron. And these electrons have a sideways overlap here, which is referred to as a pi bond. So pi bonds are generally easier to break than sigma bonds. That's important to remember. However, when you have a sigma bond with 2 pi bonds like you have here, that's a triple bond, which is quite a strong bond because it contains not only the very strong sigma bond, but also 2 of these less strong pi bonds. So the question becomes, how do you know what the hybridization will be in these? Well, in terms of the hybridization, you will know based on what's known as the steric number. And the steric number can be determined here the steric number, what this equals is for each bonded atom, that is one steric number. So we look at each atom and say for each atom that is bonded to it, we have one steric number. And if we have a lone pair on that atom, that counts as a steric number of 1. So, for example, this here is methane. This 3D structure represents methane. Oops. CH4. Can't seem to finish this H here. And so this carbon is bonded to 4 other atoms. So it has 4 bonded atoms, giving it a steric number of 4. And whenever steric number is 4, we can say that atom is sp3 hybridized. As long as there is no resonance. We do have to consider resonance in which electrons are not stuck in a certain particular location. And then we do not count them for the steric number. But we'll talk about resonance in a moment. In the case of, this is NH3 here, so it's NH3. This is the one in the middle, which is its shape is called trigonal pyramidal, which is what we see here. Here in the top position right here is a lone pair. So it has 3 atoms bonded with which are hydrogens. So this bonded atoms are 3, and the lone pairs are 1. So it is also sp3 hybridized. However, in this case, since one of the locations is occupied by a lone pair, it's trigonal pyramidal rather than the tetrahedral shape of this methane here. Here, this one's water. So this water has oxygen in the middle with 2 lone pairs, so like here and here, and it has 2 bonds. So 2 bonded atoms. Bonded atoms are 2, lone pairs are 2, so it has a steric number of 4. It's sp3 hybridized. And because 2 of those steric numbers are lone pairs, it is bent. And for situations in which steric number is 3, there's an example here. This is BF3. It has 3 bonded atoms and there are no lone pairs, so it's BF. And I'm not going to write the lone pairs on the fluorine, but there is no other lone pair on the boron. It's fine. Boron happens to be fine with not having quite an octet. So since it has 3 bonded atoms and no lone pairs, it is sp2 hybridized, and its shape is trigonal planar. You'll also get a bent shape if you have a steric number of 3 and 1 lone pair. That will give you a bent shape as well. Finally, for linear molecules, those are those molecules that have 2 bonded atoms, or a steric number of 2, which may include 2 bonded atoms and or lone pairs. One example here is ethylene, like we saw in the last one, or ethine. For this carbon atom, it is bonded to 2 atoms. Notice it's not the number of bonds that counts, the number of bonded atoms. 2 bonded atoms and 0 lone pairs, so its steric number is 2, and therefore, as we saw on the last slide, it is sp hybridized here. Okay. All right. And so I'm just going to move on to the next slide in just a moment here. Get this. Okay. Sorry, just adjusting some stuff here real quick. Kind of live adjusting here. I don't think I'm going to be able to fix it. Okay, that's fine. All right. Now, depending on the shape and the polarity of bonds, molecules may be polar. And so based on that polarity here, you will have potentially a net dipole moment in the molecule. So for example, nitrogen is far more electronegative than hydrogen, and because it's in this trigonal planar shape, the electrons are pulled towards the nitrogen, making this nitrogen side partially negative up here, partially negative, and the hydrogen side partially positive. The electrons are being pulled up this way. Likewise with water, oxygen far more electronegative than hydrogen, and it's a bent shape, and so the electrons get pulled in that direction. In addition, here we have CH2Cl2. Due to its tetrahedral shape, electrons are pulled towards these chlorine atoms, which are, so this side is partially negative, meaning the opposite side is partially positive. Important to note, this does depend on the relative shape. If we had all 4 chlorine atoms here instead, and I'll put a wedge here. The wedge means that the atom is popping out of the page. The dash means it's going into the page, which you probably remember. Due to this tetrahedral shape with 109.5 degree angles all the way around, since they're all chlorine atoms, they all pull electrons, but they all pull against each other. So there's no net dipole moment in that case. So the shape does matter. The geometry matters when determining whether a molecule is polar or not. And the reason why we care is because the polarity of the bond will affect the intermolecular forces, the attractions between molecules. And those are important to determine many physical properties such as solubility, boiling point, and others. There are three main types of intermolecular forces: dipole-dipole interactions, which only exist in polar molecules; hydrogen bonding, which is an extra strong dipole-dipole force in molecules that have hydrogen bonded to oxygen or hydrogen bonded to nitrogen in the molecule. And since those are extra polar bonds, these give you extra strong dipole forces. So hydrogen bonding is the strongest force for molecules of similar size. Dipole-dipole interactions are a second. And dispersion forces exist in all molecules, whether they're polar or not, but it's the weakest force for molecules of similar size. It gets larger for larger molecules, meaning those with more electrons in them. Boiling and melting points are larger for molecules with greater intermolecular forces, and solubility is greatest when molecules have similar polarities, when their polarities are close to one another. Now, although we talked about the hybridization and the locations of electrons and their steric number and used that to figure out the hybridization and the geometry of a molecule, we must consider the fact that sometimes electrons in a molecule are not stuck in one place. Sometimes they are delocalized, or they move around, and this is referred to as resonance. So electrons exist in orbitals, and if they're in unhybridized p orbitals, they can actually move from unhybridized p orbital to unhybridized p orbital. This is referred to as a delocalization of charge, and the charge will be spread out over more than one atom, which can sometimes be indicated with these dash lines, which indicate basically not quite a double bond, like another half of a bond. So it's like we have a 1.5 bond here on the left and a 1.5 bond here on the right. And a situation in which this might occur is, for example, if we have a carbocation here. In this case, the carbocation, if we're looking at each of these, now it appears, in this case here, this carbon here has 3 bonded atoms and no lone pairs, 2 hydrogens and 1 carbon. And so because its steric number is 3, it's sp2 hybridized. In addition, this carbon atom has 3 bonded atoms. There are 2 hydrogens here, which are not drawn in, and 1 bond to carbon. And it has no lone pairs. You can tell because it has a positive formal charge. So it is also sp2 hybridized. So each of these has an unhybridized p orbital, and those electrons can move through those p orbitals, and they actually move through all 3 of them. And therefore, those electrons are not in either of these places. So these are both sp2 hybridized with 3 bonds and no lone pairs. And if we go back to our diagram here, we see that the geometry is in fact trigonal planar. sp2 hybridized with a steric number of 3 and no lone pairs. So these are not tetrahedral. These are both sp2 hybridized trigonal planar because of the delocalization of those electrons. And in order to spot situations in which electrons will be delocalized, you will want to look for these resonance patterns. These are the 5 main resonance patterns. So when you look at a molecule and you see this, you should expect that usually these electrons are going to be delocalized. And you should be able to use arrows to show the movement of these electrons through this molecule. And this will occur when you have an allylic lone pair, meaning a lone pair that is on an atom that is right next to another atom involved in a pi bond, double bond here. And so we can have a situation where we have we show these electrons here moving and these electrons. You use two curved arrows, and ultimately, if we were to do that here for this situation, it makes an oxygen with a double bond, and now this carbon has a lone pair, and therefore it has a negative formal charge. When you're writing an alternative resonance structure, you do need to make sure that your sum of your formal charges is the same as it was before. That should not change. You're just showing the electrons that are moving, and really they're moving through this whole situation. So neither of these are the finalized structure, right? The real structure is halfway in between these. The example we saw earlier was the allylic carbocation. There's one curved arrow in that, and after that is done, now the double bond is here, and now this carbon, which had 3 bonds and no lone pairs, now has 3 bonded atoms and no lone pairs for a total of 4 bonds, because there's a double bond here and 2 single bonds. So 4 bonds, no lone pairs. Now it has 3 bonds and no lone pairs, so it has a positive formal charge to it. If you have a lone pair adjacent to a carbocation, this carbon has a positive formal charge, we call that a carbocation. Then you can use one curved arrow to represent the movement of electrons between those two states. And in this case now, our resulting resonance structure would have a double bond here between this carbon and this oxygen. And now this oxygen here, this oxygen, will have 1 lone pair instead of 2. So this is an oxygen making 3 bonds with 1 lone pair instead of 2 bonds with 2 lone pairs. So it has a positive formal charge. And note again that the formal charge, the sum of the formal charges, doesn't change. We had 1 positive formal charge before, we have 1 positive formal charge after. Same thing here, and here we have 1 negative formal charge, we have 1 negative formal charge at the end. In this case, here the resulting structure, now this oxygen had a double bond, but now those electrons are now becoming a lone pair on the oxygen. And so now it has 3 lone pairs and 1 bond, so that gives this oxygen a negative formal charge. In addition, there's one more resonance pattern in which when you have a conjugated pi bond ring, a ring with alternating double, single bonds, the electrons are moving all throughout that, so we represent that with just moving each double bond by 1 location. We didn't see this much in Chem 212, but you're going to see this significantly more in this chapter because we're going to deal with aromatic rings like this. So the resonance structure here would look like the double bond's now here, this double bond is now on the right side, and this double bond that was on the left is now over here. And so that's how you draw the arrows and the resonance structures for these. Now, how do you know which resonance structure most accurately represents the actual molecule? Well, we can assess the stability of resonance structure contributors in 2 ways. Now, sometimes there are even more resonance structures that are so unstable that we just don't even bother to write them. So, and you'll see your book do this sometime. You'll say, oh yeah, that's one of the resonance patterns, but the resulting structure is so unstable that it doesn't make sense to even write it. It's not a significant contributor. So anytime you have formal charge, that's generally going to decrease the stability of a structure, especially if that structure has a positive 1 formal charge on a very electronegative atom, such as oxygen, or a negative 1 formal charge on a low electronegativity atom, carbon, for example. Carbanions do exist, carbons with negative formal charge, but they tend to be quite unstable. And finally, complete octets will increase stability, and that's very important to have a complete octet. So if we wanted to draw resonance structures for resonance contributors for acetic acid, we can use some of these patterns here. So the first one I notice is that I have a pi bond between 2 atoms of differing electronegativity. So I can write a single arrow here and then represent this oxygen with a negative formal charge. I do have to go back to the last slide. Sorry, I did make a mistake. I missed something back here. You might have noticed I kept harping on you that the sum of the formal charges needs to be equal. And it's 0 here, but it's not here, it's negative. That's because this carbon is now making 3 bonds with no lone pairs. So there needs to be a positive formal charge there. Sorry for that oversight. This made me think of it because we're doing the same thing here, and now it's going to be negative formal charge here and positive right here, and then we have OH here. And this oxygen, because it's got zero formal charge, we can presume and correctly presume that this has two lone pairs on it. So now what I've got is a lone pair that is adjacent to a positively charged for positive formal charge carbon. So we can use this single arrow now, and we'll have another resonance contributor here. And I'm going to put my little brackets around, since that's something you generally do when showing multiple resonance contributors. And now that we're going to have a double bond to here, and this oxygen now will have 3 bonds and 1 lone pair, so now it has a positive formal charge. Now when we think about what is the relative stability of each of these, well, clearly the one on the left with 0 formal charges is the most stable. And the least stable will be the one with the positive formal charge on the most electronegative atom. So this relative stability here is most stable, intermediate stability in the center one, in the center right here, intermediate, and this one being the least stable because it has a positive formal charge on a very electronegative atom, which is not good for stability. Yeah. Okay. Now, one thing you have to watch out for is sometimes if you're kind of blindly following these patterns, what you'll see is that you might see something that looks like one of these patterns but doesn't work. And this is one kind of the quintessential example here, where you have a nitrogen. This nitrogen is already involved in a pi bond. So it's got one unhybridized p orbital. This nitrogen is sp2 hybridized. sp2 hybridized. Why is it sp2 hybridized? Well, it has it has 2 bonded atoms and 1 lone pair, so it has a steric number of 3. And in particular, this lone pair is not in a delocalized unhybridized p orbital. Why is that? Because the unhybridized p orbital is already being used to make this double bond right here. And so that lone pair must reside in the hybridized orbital, which is perpendicular here. So these electrons are not delocalized. They cannot travel throughout this series of p orbitals here. They're actually out of plane of those p orbitals. And so this is a localized electron pair, not a delocalized one. We can tell when we look at the resulting resonance structure, something looks funny about this. Generally, if we have an atom in the middle undergoing 2 double bonds, each of those pi bonds needs to be perpendicular to one another. One will go across this way, and then one will go across. Basically, if we went back to the ethyne, we can take a look. When we have 2 pi bonds on the same atoms here, there should be 2 perpendicular unhybridized p orbitals. But that is impossible given the shape in this ring. And so we can tell that this cannot be a valid resonance structure. These 2 electrons are in unhybridized orbitals. Now, let's move on here to chapter 3 and talk about acids and bases. So that was chapter 2, molecular representations. Now we're going to talk about chapter 3, acids and bases. So the definition of an acid and base, there are 2 definitions. There's the Bronsted-Lowry definition, and there's the Arrhenius definition. The Lewis definition. There's also the Arrhenius, but that's kind of like an old, out-of-date definition. So we're going to go with the Bronsted-Lowry and then the Lewis. The Bronsted-Lowry definition defines an acid as an acid gives away protons and a base accepts protons. And then we have the conjugate. The conjugate acid results when the base accepts the proton, because that's what bases do. So bases accept protons, and the conjugate acid is what you get after the acid, after the base accepts the proton. The acids give up a proton, and the conjugate base results when it accepts the proton. And so, for example, here the HCl is the acid. It's going to give an H plus over to the water. The water will accept that. It gets an extra H, and the charge goes up by 1. And the H plus is no longer on the chloride, so it goes down to a -1. Now, a lot of times we want to show the way the electrons move in order to make this H plus move from one spot to another. And that can be shown below. Here we have a terp butoxide ion, quite a basic ion. It's so basic that it can take the proton from the hydrogen. So the way we show that is we show this lone pair. These two electrons are now forming a bond with the hydrogen. And remember, this leaves as an H plus ion, which has no electrons. And so both of these electrons are left behind in this fashion. And now this oxygen, one of its lone pair electrons, this one right here, went into making a bond to the hydrogen. So now it only has two. It has 2 bonds and 2 lone pairs. So now it no longer has a formal charge as well. It's making its normal 2 bonds for oxygen. And now what's left of the water here is an oxygen with 3 lone pairs and 1 bond. So that has a negative formal charge, and that is hydroxide. When it comes to acidity, we quantify acidity based on a value called the Ka. The Ka is defined for an acid here as the concentration of its conjugate base times the concentration of the hydronium ion divided by the concentration of the weak acid initially. And usually in OChem we use the pKa, which is a negative log of that because it results in more convenient numbers like those you see here. So these tend to be very large or very small numbers, like 10 to the 10th or 10 to the -10 or something. So these are very, very large and very small numbers. When we take the negative log, we scrunch that into a lower range. The result is that the lower the pKa, it indicates a stronger acid. So sulfuric acid, an extremely strong acid, pKa of -9. If we have a protonated double bonded oxygen here, a protonated carbonyl, very, very strong acid because the resulting carbonyl is very stable. This protonated one is not. This oxygen has a positive formal charge, so that can give you an indication that this is not stable, right? It has a positive formal charge on the oxygen. It would much rather be neutral, because since oxygen is so very electronegative. Hydrohalic acids like hydrochloric acid, very strong. Hydronium, which is the strongest acid that you can have in water. Any stronger acid will give its proton to water and make hydronium. And then we have carboxylic acids, acid anhydrides, and phenol here at 9.9, then water at a pK of 15.7. You don't have to memorize these pKs. I'll give them to you when you need them. But you should be able to explain why this occurs based on a reasoning called ARIO, which we'll get to in just a moment. In terms of basicity, we can quantify basicity based on the stability of the anion and also if we know the acid, on the stability, on the reactivity of the acid or how acidic it is. The stronger the acid, the lower the pKa, the weaker the conjugate base. So bisulfide ion, extremely weak base, chloride ion, extremely weak base. However, a carbanion on an alkane, extremely strong base because the pKa of the conjugate acid is super high. It's a terrible acid, meaning it doesn't want to give away the proton. Likewise, the conjugate base really wants the proton back because it never wanted to give it up in the first place. Why is that? How could we determine or, kind of without numbers reason that a conjugate base here is very unstable? This one is very unstable. It wants to grab a proton. And this is based on a type of reasoning called ARIO, which stands for atom, resonance, induction, and orbital. And we apply ARIO to the conjugate base generally. The ion, basically, the one with a charge. So the more effectively a conjugate base can stabilize its excess negative charge, the less it's going to go and attract positive things. If that negative charge is spread out, I always compare it to a good refrigerator magnet versus a crappy one. Like if you have the crappy pizza box magnet, its tiny magnetism is spread out over this large area. And so it's so weak that it can't even hold your paper. It's very unreactive because that magnetism is spread out. Whereas if you have a tiny magnet, it's very strong, and you put it, all of its magnetism is localized in a small point, and so it sticks to the fridge very well. and it will stick your paper on the fridge very well too. The more spread out that negative charge is, the less sticky it is, the less reactive it is. And so then that it means a stable base, which means it won't go and grab back the proton, which means the acid is strong. The conjugate acid will be strong because it will give away that proton and it won't get it back easily. So let's take a look at each of these, and these are ordered in terms of their importance. Atom is generally more important than resonance, than induction, than orbital. Of course, this is a simplified way of trying to describe actually quantum mechanical things. So it fails here and there, but it generally works pretty good. When it comes to atom, there's two factors we have to consider when it comes to atom in the REO. When you're moving down a column, the atom size is the most important. The larger the atom, the more spread out the negative charge will be. And so the more stable the base will be, meaning that its conjugate acid is strong because it can produce a nice stable base that will stay the way it is. So for example, if we have a hydrogen attached to an oxygen, that will be a less acidic proton than one attached to a sulfur because of the larger atom. Or for example, if we're talking about the hydrohalic acids, the strongest hydrohalic acid is H. Oops, it's behind me here. I'm just going to write it on this side. HI. HI is the strongest hydrohalic acid because the iodide ion is the largest ion. It spreads out and stabilizes that negative charge the best. And we consider all three of these to be strong acids when they're acids, HBr, HCl, HI, because they're all stronger than water. However, HF is a weaker acid than water, and that's because the fluoride ion is the smallest, and so it's very reactive. It seeks out that H plus and grabs it back, meaning it doesn't stabilize a negative charge well. So that means HF is not a very strong acid. So HF is going to be our weakest of the hydrohalic acids because once it loses its proton and makes fluoride ion, that fluoride ion is negative and small and really wants to grab a proton back. If it finds a positive proton, it will stick to it. For atoms, as you go across the periodic table, the more electronegative the atom, the stronger the acid will be. And that's because an electronegative atom can hold on to its electrons better than one that is not as electronegative. And I know that when it goes vertically, size matters more. But when you go horizontally, the sizes are much closer to one another. They don't differ as much. So it's the electronegativity that matters. And so as you go left to right, for example, HF is a much stronger acid than water, H2O, because that electronegative fluorine atom does stabilize the negative charge better than an oxygen atom. So you should be able to predict the patterns here now. So you can see that HCl being a very strong acid due to the electronegative large chloride ion. And when we look at, for example, this one, or the conjugate base will stabilize that negative charge on the oxygen atom, and there's going to be resonance. So let's look at that next step. Besides atom, there's resonance. So if we're talking about the same atom, what matters next is resonance. So if we deprotonate the acetic acid here, if we deprotonate the acetic acid, we get this product. So now basically these electrons get left behind, and we have an oxygen with 3 lone pairs and 1 bond. So it has a negative formal charge, and now we have a lone pair that's allylic lone pair. So we have resonance here. And so that resonance spreads out the negative charges and stabilizes the conjugate base. Whereas when we have ethanol here, there's no resonance. There's no allylic lone pair. And so acetic acid is a stronger acid than ethanol because the resonance of its conjugate base spreads out that negative charge and makes that conjugate base less reactive in terms of grabbing back the proton. Induction. So induction is another way that the negative formal charge can be stabilized. Induction occurs when you have many electron withdrawing groups, meaning highly electronegative groups, on the carbon atom that is next to the carbon atom attached to each of these oxygens, so the deprotonated. So here we can see that this carbon atom is 1 carbon away from the one attached to the oxygen that's deprotonated when it's an acid. So it only works 1 carbon away like this, 1 carbon away from the carbon attached to it. And we can see, though, that the pKa for the trichloroacetic acid here is much lower, so it's much more acidic than the one without the chlorine atoms. And this is because this electron withdrawing effect helps to spread out that negative charge even more and make for an even more stable conjugate base. Finally, orbital is the last one. So in terms of hybridized orbitals, because sp3 uses the most orbitals, it's got the largest orbital size. Here uses 1 s orbital and 3 p orbitals. The sp2 orbital is smaller than that, and the sp orbital is even smaller. So remember, we're talking about the spreading out of this negative charge. So the larger the orbital, the more spread out that negative charge will be, and the more stabilized it will be. And so those atoms here that are sp3 hybridized tend to stabilize that negative charge more than atoms that are sp2 hybridized, more than those that are sp hybridized. And so, for example, as an example of this, if we're talking about if this carbon atom here has a lone pair and 2 hydrogens, and it is a carbanion, it will stabilize that negative charge, not as, whoops, I misspoke there. That negative charge here is actually going to be closer to the nucleus. Oh, geez. Sorry, it's held closer to the nucleus. Please scratch that, what I just said. I kind of confused that for the last one. But in terms of the nucleus is right here. So this factor is actually how close these electrons are to the nucleus. So when it's very close, it can be more tightly held and better stabilized. So it's like the highly electronegative atom. I can't believe I did that. But anyway, if we have a carbon atom like this, I'll just kind of point you back to this this guy right here. We can see that if we look at a negative formal charge on this carbon, its conjugate acid is more acidic than that produces a carbanion on the alkane, not on the carbon double bond. And this is because the sp2 hybridized carbon here has a smaller orbital, so that negative charge is held more closely to the nucleus and is thus doesn't get away from the atom as easily. It stabilizes it more. Whereas here, it's in the larger sp3 orbital. So this is, sp2, this is sp3. And therefore, those electrons get farther away from the nucleus, and it's easier for them to get away and make a bond. So when it comes to atom size, let me clarify what I said too. When it comes to atom size, the larger atoms will spread out that negative charge a little better, which stabilizes the negative charge. But when it comes to orbitals, what's more important is the proximity of the electrons to the nucleus. And so those that are close to the nucleus will be held more tightly, thus stabilizing the negative charge better than those in an sp3 orbital, for example, where the electrons are way out here, way out here. I could use a different color here for this, so it would be a little bit better. Whoops. Okay. Go back. And so if the electrons are way out here and the nucleus is here, they're not held as tightly as if they're here, and so they're not as well stabilized. And that's how we determine the relative acidities of these. So when we look at a situation like this one, we have an acid here. This is the acidic proton right here, this hydrogen, and this is going to be given away over to this nitrogen. And what we can see here is we have molecules that also have resonance. If we look at this molecule, all of these are on nitrogen, so we can't consider atom right away, but we should think about resonance. So here we have a couple of patterns here. We have atoms of differing electronegativity, and we have an allylic lone pair. And so both of these combined go to produce a resonance structure that looks like this, with the negative formal charge on the sulfur atom. And there's a nitrogen, and now this has one lone pair, so it has no formal charge. So these are in resonance from one another, and this one also has resonance, but what you can see is on that resonance structure, this electron will be held on an oxygen atom, which does not stabilize the negative charge as well as the sulfur atom due to its larger size. So what we're going to see is that the acid that contains a sulfur atom, that when it loses its proton, makes this conjugate base, this is going to be a more stabilized conjugate base. So that makes this one the stronger acid, and this one the weaker acid. And so this reaction will go in the leftward direction. So these reactions proceed from the stronger acid and base to the weaker acid and base. So since due to the resonance situation that results in the negative charge being held on the sulfur atom and being greatly more stabilized by the greater size of the atom, that makes this the stronger acid with the sulfur. This one on the left is a weaker acid. And the reaction always proceeds from the stronger acid to the weaker acid. So this one would favor the left side. Finally, we have Lewis acids and bases. A Lewis acid is one that accepts and shares a pair of electrons. A Lewis base is one that donates and shares a pair of electrons. So in this case here, we have this Lewis base here is donating the electrons, making this the base. This boron trifluoride is accepting the electrons, making this the acid. So this is an acid-base situation in which there are no protons transferred. However, it's still considered an acid and a base. And so this is another version of that, another associated definition of acid that you may come up from time to time. And that's going to wrap up chapter 3. So in my next video, I'm going to start talking about chapters 4 through 6. That will be another half-hour or so video, and I'll see you in the next one. Bye.